Ladies and gentlemen, do this now. I challenge you. Find a book at home, find a piece of paper at home, and try this out. I want you to slowly pull, well, first of all, put the paper into the book like this. Okay, just like this. And it says slowly pull the paper under the book. Observe.
Ooh. Book move. How you make book move?
Okay, step 2. Pull the paper on. Whoops, wrong. Pull the paper under the book as fast as you can. Observe. As fast as I can.
Wow!
Okay, let's try that one more time.
That was cool.
That was good, huh? As fast as I can. What is going on here?
I know.
My first question for you guys. How are Newton's first and second laws at work here? Well, let's think about what are Newton's first and second laws. Let's start with number 1. So his first law, an object at rest will stay at rest unless acted on by an outside force.
Object at rest.
Staying at rest, not moving, no outside forces. Oh, let me just go ahead and put my outside force on this object at rest. What's happening here? So we have a book here, and the book has mass, therefore it has inertia, and it doesn't want to move. However, there is a connection between the paper and the book that we're gonna call that the force of friction.
Yeah.
Right? And so when I pull the book, how is it moving? Well, it's moving because it's touching the paper, and there is a force that the paper is exerting on the book, and the book is exerting on the paper. So what we have here is we have an object that's at rest at first, and then I'm exerting a force on it and moving the book.
Yep.
Second law, Newton's second law.
What does that look like? Isn't that an equation?
Let's go ahead and take a look. So force net equals mass times acceleration. Okay. So if we have a small acceleration with the same mass, then we only need a small force to make it move.
That wasn't a very big acceleration when you were pulling slowly.
No, right? So example here. So if we have a really small acceleration, okay, the force can be really small as well.
Yeah, it only takes a very small force of friction.
The force of friction really small. But however, if I have, my mass is the same, a really big acceleration, it takes a really, really big force to make it move, right? So here, my acceleration is really big.
Boom!
Right? And the force of friction is not big enough to make it move with it.
Oh.
Okay, so I'll do that one more time. Okay, when I'm moving the book slowly, my acceleration is slow. My force, in this case, the force of friction, it's small enough
To cause that acceleration.
to cause that acceleration, yeah. But when I have a really big acceleration,
Boom!
okay, I need a really big force that I wanted to keep it with it. But the force between the paper and the book is just not big enough.
It's not enough.
It gets left behind.
Sweet.
Sweet. Can Newton's second law be used to define inertial mass?
Define.
Huh.
Well, there's Newton's second law.
Okay, here's Newton's second law. Now, inertia. What did that have to do with again? Inertial mass? Mass.
Mass.
Right?
Oh.
Okay, so if I wanted to solve this for mass, it would look like this, right? And so inertial mass is essentially the amount of force per unit acceleration that we have.
I like that.
So the greater the force, the greater the acceleration. The less the force, the less the acceleration. And so what we have here is we have a definition of inertial mass. Let's relate this back to our hacksaw lab. So in the hacksaw lab, we added the washers to the hacksaw, and we were trying to figure out how that affected time, right? And the more washers that we added, the slower that it went. So more mass is slower time, which really means less acceleration. So what does it have to do with this? Let's take a look at this fraction, 1/2. Well, 1/2 equals 0.5, right? So let's pretend like 0.5 is our mass, and you can see, well, actually we'll go over here, and we'll look at quarter, 1/4, x equals 0.25, right?
That's a smaller number.
It's a smaller number. So if you think about these two numbers as being our mass, okay, 0.5 versus 0.25, then you'll see that if these numbers on the bottom represent our acceleration, that the more mass we have, the smaller the acceleration.
Yep.
Right? This is a 4, this is a 2. So having a larger, a smaller number here gives me a larger number here. Okay, so moving on here. Free body diagrams. So this is a free body diagram.
How can you tell?
You can tell because you have the dot here in the middle representing whatever your object is, and we have these arrows that are both coming out of that free body, that dot right there.
Tails are on the dot.
Both of the tails are on the dot, yes. And so, for example, that could be force 1, that could be force 2. How is this different from vector addition? Well, first of all, there's no dot here. And second of all, our forces are being added head to tail. So we have tail, here's my head, and then this head is attached to that tail to create our resultant. So in this one, okay, both of the tails are attached to the dot.
That's free body diagram.
Free body, okay? Here, vector addition, this is being attached head to the tail right there.
You're going to have to be able to do both.
Yeah, okay. Did the Hacksaw Blade Lab illustrate inertial mass? I'd like you guys to, on the next page, there's going to be an assignment for you to answer this question on. You're going to write me a paragraph illustrating this, answering this question, and you should answer these 3 questions within that paragraph. What is inertial mass? What did we do in the Hacksaw Lab? And how did that illustrate inertial mass? Good luck. All right, so you guys are gonna go ahead and go to page 113. And what you're gonna do is you are going to draw a sketch of what's going on, write the variables that you are given, write the equation or equations that you will need to use, and then solve it over here. And so I'm talking about page 113, starting with number 2. Good luck.